let's extend higher roots to some variables. And really this is related to everything we've been talking about, but also the Orndorff method will come in real handy here. So we have the square root of x squared, and this is just x to the first. For one reason, because a square root undoes a square, but because of the Orndorff method, a way to think about it is 2 goes into 2 once, so that's why it's x to the first, with nothing left over. The cube root of n cubed, well, it's just n, because a cube root undoes a cube, but also because of the Orndorff method, 3 divided by 3 is 1, with nothing left over. The fourth root of p to the fourth, it's just p, for all the same reasons that we talked about, and the fifth root of y to the fifth is just y. Let's take this a step further though, right, because you guys can handle more than that. Let's say we were considering the cube root of y to the 18th. Well, this is where the Orndorff way of thinking is really helpful. 3 goes into 18 6 times, so this would be y to the 6th with nothing left over. Now let's contrast that with the cube root of y to the 19th. Well, 3 goes into 19 6 times with 1 left over. So since it goes in 6 times, this would be y to the 6th times the cube root of y to the first, because there would be 1 left over. Let's try one more like that. The fourth root of z to the 8th. Well, that would just be z squared, because 4 goes into 8 twice. Take this one step further. The cube root of 64 p to the 6th. Hopefully you're starting to notice that 64, besides being a perfect square, is also a perfect cube. 64 is 4 cubed, so that's why it's just 4. And the cube root of p to the 6th would be p squared. Last thing for our purposes right now, try it yourself. The fourth root of 16 q to the 12th. Hit pause and see what you can do. Well, the fourth root of 16 is 2, and the fourth root of q to the 12th is q to the 3rd. Hope you're doing well.